Hello, I'm going to present optimizing ciphertext management for faster fully homomorphic encryption computation. This work I did with Oleg Mazonka and Mihail Maniatakos from New York University. So first, let's define what fully homomorphic encryption is. It's a special type of encryption that you let you operate directly in the encrypted domain. Here we have an example. We are adding two plaintext, M1 and M2. And if there's an operation that can be done on the encryption of this plaintext such that when we decrypt, we get the same result as adding the plaintext, then we have a homomorphic operation. This is different than traditional crypto systems like AES, where you can protect data at rest and data in transit. But if you need to do any processing in this data, you need to decrypt first. So the good thing about FHE is that it's very useful in the context of outsourced computation. When a client has some private data like an X-ray and wants to use the service of a service provider that can tell if you have cancer or not. The thing here is that the client doesn't want to share its sensitive data with the service provider, but also the service provider don't want to share its IP with the client. So with FHE, the client can encrypt its X-ray, send to the server will do computation in the encrypted domain, send the ciphertext back to the client that can then decrypt and check the result. The issue why FHE has not been widely used yet is because it is very slow. It's many orders of magnitude slower than unencrypted computation. So there are several efforts to make it faster. For example, you can improve the crypto system by itself, the underlying math of the crypto system. You can create hardware accelerators for this crypto system. You can improve the code of FHE libraries that implement this FHE scheme. You can create compilers that can take the arithmetic circuits generated by FHE applications and optimize them using classical or new compilation techniques. Or you can change the way you create the application to use more efficiently the operations provided by FHE. In this work, we focus in the higher level. So let's first see how FHE applications are built. You have an FHE scheme that is implemented by some FHE library. A compiler can use this FHE library. And then there is an application. The application will either use an FHE compiler or use the FHE library directly. Both options are commonly used. What we propose here is a framework that sits between on top of the FHE library, and it's just plug and play, and it will provide some performance improvement. So let's see the features of this proposed framework. So it's a plug and play framework. You just put it there. It works as this middleware between FHE compilers and libraries. It can be also used directly by the application. In this compiler, we have a smart ciphertext management that handle better data movement. We have employ some caching techniques that reuse operations. So the goal of the compiler is to reduce data movement and computation. Based on our experimental results, we see 2x performance improvement in fully connected layers and 24x in convolutional layers. Very importantly, it requires no code modification. So the same code that works with an FHE library will work on our compiler and provide this extra performance. Let's start first with ciphertext management. So first thing is that ciphertexts are very large objects. FHE ciphertexts are in the megabytes. And handling this object, like creating this object, moving, destroying, copying, it's very costly. And the thing is that the compiler will can create temporary objects that this can be outside of the programmer's control. So this creation, copying, moving, destroying of temporary objects will degrade the performance because the objects are large, are not small. So this is not a problem for the native data types because they are like 64 bits. But when you have things in the megabytes, then it becomes significant. So to solve that, we propose this automatic ciphertext reference module where we replace a ciphertext by small unique identifiers, and we operate on these identifiers. So here I will show an example of how this module works. So we have here on the left the default computation that would be done without our module. Here we have our reference module, and here we have the example that we will be executing. So the first operation, we copy the value of A in the default configuration. So we need to create this large ciphertext. And in our reference module, we just both will have the same ID. So the ciphertext, underlying ciphertext, will be only one object. Now we have another operation, also copying the same object. We need to copy again in the default, but here we same again, just a reference. Now we go out of context, so we need to destroy this large object, but here we just need to destroy a small 64-bit reference. Now in this case, the computation is exactly the same. We do the homomorphic operation to create this temporary object. Now when we assign to A, in the default, we have the move constructor, which has the same cost of changing the reference, but in the default, we also need to destroy the original object. So these are the things that this module provide. The other thing we do is the operation optimization module, where here I will start with an example. So we have a vector matrix product of an encrypted vector plaintext matrix. And we can see that some operations here can be reused, like for C1, it's reused, 2C2 is also reused. This could be easily solved by compilers like homomorphic expression elimination, but the thing is that in FHE, plaintext values are usually loaded through serialization, so they are only available during computation. You don't know them at compilation time. So we want to do this optimization, and we will need to do it then dynamically. So for that, we create this operation optimization module that avoids these repeating operations. This module has a data structure where we have a table where we store identification of operations. So for example, this would be for 4 times C1, we would have here the multiplication of the identification of ciphertext C1 and the plaintext 4. So when we are going to do this operation, we check if this value is already in this module. If it is, we return. If it's not, we compute and add in the table. And this module is a sort of data structure that mix hashes and queues. It's well described in the paper. The thing is that when we use this module, we can reduce this operation that would take 8 ciphertext plaintext multiplications and 4 ciphertext additions to only 2 ciphertext plaintext multiplication and 1 ciphertext addition. Here I'm going to show how it works. So we start the table with the input values, the C1 and C2. We compute the first multiplication and we add to the table. Compute the next multiplication, we add to the table. Now we compute the addition, but the other values, they stay in the table with the temporary values. We don't destroy them. And then we add also the addition to the table. Now the other operations, we don't need to do any homomorphic computation here. We just need to find them in the table. So this speeds up a lot the computation because we save many homomorphic operations which are costly. The thing is that you can notice that as we do more operation, this table grows and grows. So we can set a size limit for this table, and we can discard older values as the table reaches this limit. To evaluate our proposal, we compare baseline implementation in Microsoft Seal BFE. We compare against our framework with the reference module enable, only the reference module, and also against our framework with both modules, the reference and the optimization module in it. We have 3 benchmarks: fully connected layer, convolutional layer, encrypted convolutional neural network. In all cases, the input is encrypted and the weights and biases are plaintext. We select the dimensional size to match commonly used data sets like Cipher and ImageNet, and also to match commonly used sizes from machine learning models like AlexNet and ResNet. We test for different table sizes. And as a note here, we have the operations, the homomorphic operations that are used for in fully connected layers and convolutional layers are ciphertext plaintext multiplication and ciphertext addition. And in the case of the CNN, we have an extra operation that's ciphertext squaring that's used in the activation function. So here first we have the results for the fully connected layers. We show for two cases, 256 by 256 multiplying square matrices, and here 1024 times 1000 by 1024 matrices. We have execution time, memory, number of ciphertext copies, number of multiplications, number of additions, and the cache hits. So first, we see that here the baseline implementation in gray, and we see that reference module only it in black. So you can see there is a performance improvement here and also performance improvement in the larger matrices. And this is due to reduced number of ciphertext copies. You can see here. In the same case, the same happens here. When we use the OOM to cache, we have two cases here. We cache the multiplications, and here we cache both multiplication and additions. When we cache multiplications, after when we are caching, we need to allocate more memory for these operations that we are caching, so it has some cost. So the number of reductions in the number of operations has to compensate for this allocation. We see that this happens when the table size is large enough for the multiplication case in green, and this is because it reduces here a lot the number of ciphertext multiplications. In the case when we have addition, the reduction in addition is very small, so it doesn't compensate for the extra cost to allocate this memory. And for the larger matrices, we see the same thing, but with more benefits of caching because the reduction is more significant. In the case of the convolutional layer, we also have two cases, one with a channel output, one that has 8 channel outputs and a filter size of 3, and the other that 32 channel outputs and a filter size of 7. Here again, we see the baseline and the reference module only. We see that the reference module is also faster in both cases, and also it's for the same reason that's reduced the number of ciphertext copies. We see in this case that caching has a strong effect in both cases, only when we cache multiplications, when we cache both operations. And this is because the number of operations reduces a lot. We see that the number of operations reduce, the number of multiplications reduce a lot in both cases. And then also the number of additions reduce a lot in both cases. That's why. And very interesting is that the number of ciphertext copies is even lower than the reference module. And this is because we reuse so many operations. And we can see that as we increase the size, the number of channel outputs, or as we increase the filter size, the performance improvement of caching becomes much more significant. Like you can see here from this graph, you go from around 120 to around 1015, and here you go from more than 2000 to let's around 50. So we expect to see more improvement as the dimensions grow, because there is more, the chance of reusing data is higher. Here we have the CNN. I break down by layers. There are more layers, but I'm showing the ones that have important information here. We compare also against the baseline, the reference module only, and when we use both modules for caching only multiplication, addition, and squaring. So we have here convolution followed by addition, the square, which works as the activation function, then mean pool, which is tries to do similar task as max pooling, and convolution addition again. Here we see that the baseline takes 102 seconds, and reference module it goes down to a little lower than 59, which is similar to caching only plain text, ciphertext plain text multiplications. So here we see that these two have the fastest time for this, and when we try to cache additions, it becomes lower. There is no squaring here, so these two are equivalent. In this case, when we do squaring, the square operation, there are very few of them compared to the total, around 5,000, little more. And other operations are like in the hundreds of thousands, so there are very few squares, but they are very costly individually. So it means that the cost of allocating memory becomes less significant here, right? And that's why we don't see much difference in the execution time here. And when we go to another thing that's interesting, when we go to the next convolution layer, we also see this performance improvement of using only the reference module, but we see also a benefit of caching. And the reason is because this layer has 10 channel outputs, and this layer has 5 only. So as you increase the number of channel outputs, you get more performance from using the caching mechanism. And this shaves around 90 seconds from the total execution time. So to summarize, we propose this plug-and-play framework that can accelerate FHE computation, and it does that by using with techniques to do smart ciphertext management and some caching techniques. This reduces the data movement and also the number of FHE operations. And we saw that it gives around 2x performance improvement in the fully connected layers and 24x in the convolutional layers. Thank you.